ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last time we discussed some aspects of the compound semiconductors, and we saw that there are 2, 6, 3, 5, 4, 4. We have named all of them, and we finally came to the ternary compound semiconductors, and we have also discussed everything about, or most of the things about 3, 5 compound semiconductors. Now, we just began our discussion on ternary compound semiconductors. Okay? So, that is why this lecture will be on ternary compound semiconductors and some of their applications, because it is interesting to see, instead of just listing out those materials, see where they are useful. In fact, you will see that the emphasis on some of the devices or materials is on photonic devices. That also we will touch upon. So, now you can see that here this is the entire picture of the ternary compounds and compound semiconductors given. Actually, what you see is mainly 3, 5 semiconductors and 2, 6 semiconductors joined by some lines. So, you can see, to go from the top, you have here all these compounds are the 2, 6 compounds, which we have virtually eliminated from the microelectronics agenda, because their mobilities are low. Their band gaps are excellent, much higher than that of silicon in all cases, but we do not want it for microelectronics, but they are useful for optoelectronics or photonic devices. Now, let us see the ternary compounds. You can see here in this diagram, just I want to tell you something about this diagram. You have on x axis the lattice constant of each of those materials. Okay. See, for example, if you see gallium arsenide, it is about 5.63 angstroms or 5.65 angstroms or so for gallium arsenide. Now, if you see indium arsenide, it is quite different. Okay. You can see it is more than 6.1, slightly less than 6.1 angstroms, bigger atom. Indium is bigger compared to gallium. Okay. Gallium is 1.26 angstroms, indium is 1.44 angstroms. So, that way it is bigger, that way the lattice constant is big, okay, compared to that. So, on x axis you have that. On the y axis you have the minimum energy band gap. And it is a minimum energy band gap. The meaning is, it is actually the band gap which is coming into picture. You have seen yesterday that there is direct band gap, there is indirect band gap also. There may be both band gaps, minimas in the conduction band. What we talk of is the minima of the minimum, minimum of the minima. There are two minima which is lower. So, that is what it is called. It is actually the band gap. Okay. So, okay, that is exercise. On the right hand side, you see the wavelength. Okay. This is the wavelength that corresponds to the band gap. Okay. If it can emit light, it will emit light corresponding to that band gap. Guided by the formula, energy is equal to h nu. So, if you substitute for h and nu is equal to velocity by lambda, lambda will be related to energy as we will write down that afterwards 1.24 divided by energy. So, this number that you get here on the right hand side is actually is 1.24 divided by the band gap, okay, in microns. When you express energy in electron volts, that will be in microns. Okay. If you want, you can write down that. See, for example, E is h nu, where nu is the frequency, h is the famous law, you can't forget, Planck's constant. That is equal to h into the velocity of light. To avoid confusion, I am putting c divided by lambda, wavelength. Okay. Therefore, lambda is equal to h c by E. You substitute c is velocity of light, okay, and h is Planck's constant. You substitute for those two quantities together, and then this turns out to be, in fact, it is worthwhile remembering the relationship between energy and lambda, 1.24 divided by E. So many microns, okay, where when E is in electron volts. So, you can see if gallium arsenide has got band gap of 1.43 electron volts, automatically you will know how much is the lambda corresponding to that is. It will actually be equal to about 0.87 or so, the wavelength corresponding to that, okay, divide by this 1.24 divided by 1.43, about 0.87 wavelength. So, if you use gallium arsenide for realizing light emitting diodes, how do you make light emitting diodes? Make a p-n junction. You make a p-n junction, forward bias it, pump in current, that injects carriers into the, for example, if it is a n plus p diode, electrons are injected into the p region. Those electrons are minority carriers which will recombine, and when it recombines, the electrons drop from the conduction band to the valence band. So, if your energy band diagram is like this, okay, and that is the satellite valley, which is the gallium arsenide. So, if I have this as 1.43 electron volts, that is gallium arsenide, you will have this as 1.8 electron volts. You do not care about that, because the electrons tend to occupy the minimum energy position, that is that. It will not occupy this position unless you give enough energy by some external means like electric field, then you can scatter it from here to here, otherwise it will remain here. So, if you make a p-n junction like that, okay, n plus heavily doped n region and p, and if I forward bias that and pump in current, okay, if it is gallium arsenide device, the electron or whatever, gallium arsenide or silicon, it will inject electrons into this. Those electrons will be recombining by dropping down like this. Okay, recombination means electrons getting recombining with the holes. So, transfer of electrons from the conduction band to the valence band. Current diode is forward bias, just okay, overside there. So, you forward bias the diode, current is injected, and when current is injected, electrons are injected. When current is flowing actually in this direction, okay, that means electrons are injected into that region, p region. So, electron injection is in that direction. So, they will recombine. When they recombine, they lose the energy, and that energy is given to the light. That is a light emitting diode. Now, if you use gallium arsenide, the wavelength that you get will be actually 1.24 by E, that is about 0.87 microns. 0.87 micron is something which you cannot see. It is not a visible light, it is infrared radiation. So, it cannot be used for making light emitting diodes. Okay? But the wavelength that is projected here on the right hand side of this diagram is actually the wavelength corresponding to, if there is a transition like this, that wavelength corresponding to that, corresponding to the band gap. Okay. So, let us see, and this diagram that you have drawn is actually a diagram for gallium arsenide direct band gap, and also we have said the minimum band gap that is put there implies that this is the minimum compared to that. Okay. If you transfer the electrons from here to here, if they were there, then it would have been indirect transition. Okay. So, I am just trying to point out some of these things which are in this diagram. So, on this side you get that wavelength which is actually 1.24 divided by energy. Now, you can see there are number of things put here. Gallium phosphide, it gives what is its lattice constant is, it gives what is the band gap for that is, okay, minimum band gap. Then you have got gallium arsenide here. Now, between those two, gallium phosphide and gallium arsenide, a line is drawn. In fact, between each of those semiconductors, 3-5 semiconductors in this diagram, lines are drawn. Some of them are solid lines, some of them are broken lines. Okay. Now, let us take this gallium phosphide and gallium arsenide. You can make a compound which consists of gallium, arsenic and phosphorus, gallium arsenide phosphide or gallium arsenic phosphide, whichever way you want to call it, ternary. So, what is shown here is you can make ternary using gallium phosphide and gallium arsenide. Now, remember, gallium arsenide is a direct band gap semiconductor. We have explained all that, direct band gap semiconductor, whereas gallium phosphide is an indirect band gap semiconductor. So, if you mix them together, what happens is the mixture of them, for example, if you take here, that is gallium arsenic phosphide, okay, into the, if you see that, this is solid line, implying from gallium arsenide is direct band gap. If I go on adding phosphorus to that gallium arsenide, it becomes more and more towards gallium arsenic phosphide. If you go all the way down, it is gallium phosphide, that becomes indirect band gap. That means, from the direct band gap material, it will move towards the indirect band gap semiconductor. At some point, it will become indirect. For example, there it becomes indirect. Beyond that point, if I move, that dotted line indicates that that will be indirect band gap. The solid line indicates it is direct band gap. Take a look at this, for example, gallium arsenide, direct band gap, indium arsenide, direct band gap. We can make alloys of gallium, indium arsenide, ternary compound consisting of gallium, indium and arsenic, that is called gallium indium arsenide. Now, you can see the band gap of gallium arsenide 1.43, band gap of indium arsenide is something like 0.36. You can mix them together, you can get material whose band gap is anywhere from 1.43, right down to 0.36. Whether you are interested in that band gap, whatever it is, that depends upon your particular application. For example, I can just adjust the concentration of indium. This is gallium arsenide. I keep on adding indium to gallium arsenide, they replace gallium with indium, increase the mole fraction of indium, then at a particular point it reaches here. Now, you can see a solid line is made here, that is, you can use that compound. The entire thing is solid line here, because the entire thing is, because indium arsenide is direct band gap, gallium arsenide is direct band gap. So, any combination is direct band gap. Now, we can have here indium phosphide, which is actually slightly higher band gap compared to that here, that is also direct band gap. I can mix gallium indium arsenide of this composition, okay, with indium phosphide, or I can grow gallium indium arsenide on indium phosphide. See that vertical lines indicate that there is a lattice match between the two compounds. This diagram is actually, I have just one slide here, contains so much packed information here. So, you can see here this material at this point, it has 5.85 or something like that, lattice constant. If you take indium phosphide, the line is vertically up, it has the same lattice constant. So, I can grow gallium indium arsenide of that composition on indium phosphide. The vertical lines indicate that they are lattice matched, and you can grow one over the other. Similarly, here you can see, and the whole thing is of course direct band gap. Similarly, here you can see gallium arsenide. Lattice constant is practically same as that of aluminum arsenide. We can mix gallium arsenide with aluminum arsenide. Aluminum arsenide is indirect band gap. So, if I mix that, when you go up increasing aluminum content, it becomes from direct to indirect. Okay? But again what you are telling is, you can have gallium arsenide, on the top of that you can have a compound made up of any composition from here to here. On the gallium arsenide, I can have aluminum gallium arsenide, that is keep on adding aluminum to gallium arsenide, it becomes aluminum gallium arsenide. I can have that. So, it looks at this stage that we are just playing with the different materials, but that is the technology for compound semiconductors. You can mix compounds, realize whatever band gap you want, okay, and you can use one material of one band gap, for example 1.43 here, mix with aluminum arsenide whose band gap is something like 2. So, 1.43 band gap gallium arsenide, aluminum gallium arsenide band gap of 2, you can make one substrate of one material, maybe that is n type, that is an example. On the top you can have aluminum gallium arsenide which is p type, or you can take p type gallium arsenide and n type aluminum gallium arsenide, that is a heterojunction. The conventionally what we talk of is silicon on silicon, silicon p type material, silicon n type material, that is a homojunction, material is same. But if you have gallium arsenide p type, aluminum gallium arsenide on that n type, that is a heterojunction. So, you can make heterojunctions, but we should be careful when you are making heterojunctions. What is the thing that should be careful? Lattice match. So, that is why you should go up and mix for making junctions vertically down like that. Okay. Now, let us take a look at some of the materials which are useful for photonic applications. For example, light emitting diodes, maybe lasers. Okay, I will just take up this example where you mix gallium phosphide and gallium arsenide. Let us draw that diagram now. So, I will take this diagram out. Okay, let me redraw this here. So, you got gallium arsenide, satellite valley, the energy versus momentum, okay, and conduction band, valence band. That is understood. So, it is a direct band gap semiconductor, and then you have got this is 1.43. I am rewriting whatever I have written there earlier, and this quantity is 1.8 electron volts. Okay. Now, the lattice constant A hereafter I will write only A, means lattice constant, which is 5.653 angstroms for gallium arsenide. Now, you take a look at the other material, that is gallium phosphide. Okay. The gallium phosphide has got, it is an indirect band gap material. So, that has got, okay. So, see this here, you have got gallium phosphide which is coming like that and something like this, and that is actually 2.8 electron volt. That is 2.8 electron volts. It is not a direct band gap semiconductor, it is an indirect band gap semiconductor, which would mean you will have a satellite valley which is below that. So, that is actually somewhere here. So, that is 2.26 electron volts. Okay. And A for this case is actually 5.45 electron volts, angstroms, 5.45 angstroms. So, that is shown also in the diagram here, the values are shown there, okay, 5.45 and 5.653. Now, let us see what would happen if you mix up these two. Okay. So, let us put this diagram. You can see when you mix these two, you can get a material called gallium arsenic 1 minus Y phosphide. You can mix them, you can get the ternary compound, which is very useful for light emitting diodes. Now, let us put that diagram here. So, on this side I have got gallium arsenide, I will vary Y, that Y. Okay. When Y is equal to 0, that material is gallium arsenide. Okay. So, that is Y equal to 0, that is gallium arsenide. Then when Y is equal to 1, that is gallium phosphide. Okay. And the whole material here you can call it as gallium arsenic 1 minus Y phosphide Y. What you are doing is go on adding phosphorus to gallium arsenide. So, disturb the stoichiometry to get the total number of arsenic and phosphorus atoms equal to gallium atoms, that is the stoichiometry. Okay. Now, you can just see, put this X here, you will represent energy gap E g. Let me put it like this. Okay. Energy gaps. In electron volts, that is what is put there. Now, you plot this, put that number there. Okay. You can put this is 1, 1.5, 2, 2.5, 3. Now, if you take a look at the gallium arsenide, you have got direct band gap of 1.43. Okay. That I will mark it as here. I will put it with some color here, 1.43. And if you take a look at this gap, that is 1.8, that is somewhere here. Okay. That is 1.8. So, I mark those 2 points there. If you go to the other end, gallium phosphide has got 2.26 as the indirect band gap. So, I can just put it down here like this. okay, 2.26 somewhere here, that is actually the indirect band gap. Okay, that is actually the band gap of gallium phosphide. So, if I make y equal to 0, the minimum band gap is 1.43. If I take y equal to 1, the minimum band gap is 2.26, direct band gap, indirect band gap, minimum band gap. Okay. Now, what happens is when you mix them together, the lattice constants almost linearly changes. Similarly, the interaction between the two takes place. Without getting down into the physics of that, what happens is the direct band gap links with the direct band gap here almost linearly, not exactly linear, almost linearly it varies. So, that means actually if I mix, and this direct band gap here is 2.8, okay, you have got 2.8 there, 2 point something. So, when you mix them together, what turns out is from here to there you will have the band gap, this keeping on widening, ultimately it becomes that. This whatever 1.8 is there, that keeps on widening, ultimately becomes that. Okay, let us plot that. So, this is almost linear from here to here, almost linear. Okay, that the direct band gap varies like that, because the lattice constant almost linearly varies. Now, the indirect band gap corresponding to that, this latches on to that also will vary linearly. So, what you have finally is something like, I am just trying to keep track of where that 0.5 thing is. Okay. So, somewhere here, that is the indirect band gap will vary from 1.8 to 2.26, and here it is 2.8. So, it is very interesting to see, as you keep on varying that y, the difference between this and this narrows, and at a particular point the direct band gap and indirect band gap both remain same. That means actually electrons will be there, some of them at here, some of them will be there in that point. So, transition can take place from either of them. So, but most interesting part is, if you see this, the combined, which is actually a band gap now. Here the band gap is this one, minimum band gap, direct band gap. If you go here up, this is indirect, that is indirect, and this one is direct. Okay. So, if you vary the band gap, ultimately what you get is that is the minimum. So, up to that point it is direct band gap. If you go into this, you move from gallium arsenide towards indium phosphide, up to that point it is direct, beyond that point it is indirect. What has happened? From here, between the two band gaps, this is smaller. So, it turns out to be like this. So, the final band gap of this material will vary from 1.48, 1.43, and at this point it will be 1.97. Okay, here that will be 1.977, and this will be actually 0.45. So, when the okay, let me just clean it up here, this is 0.47 or 0.45. When y is 0.45, the transition from direct to indirect takes place. That is the key thing here. So, the most interesting part of this diagram is, or this exercise is, you can make make use of ternary compound semiconductors by mixing binary, whether it is direct or indirect depends upon the composition. Here Y, that is the phosphorus mole fraction, as vary from 0 to 1, you will go from direct to indirect. What is the key thing here? Now, you can actually use, if I want to make light emitting diode, which portion of this diagram will we use? The answer will be immediately spontaneous, because direct band gap. Direct band gap gives transition like that. Indirect band gap, actually transition like this will not emit light, because last time we mentioned it will be in a two-step process, because momentum difference. So, so if there are no intermediate levels, it will be this portion which you choose. So, what people have done is they have made use of Y equal to 0.4 somewhere here, Y equals to 0.4 gallium arsenic phosphide. If you take, that gives you Eg equal to 1.87 electron volts. Here, somewhere here, 0.4, and that is 1.87 direct band gap. You make a diode with that, PN junction with that, it can be used for a forward bias, it can be used as light emitting diode. What is the wavelength corresponding to that? 1.24 divided by 1.87, so many microns. So, lambda optical emission for this case actually turns out to be 0.66 microns. What is that? That is red. So, that is red light. I am overwriting here, but you have got red light. So, you can red LEDs, you can make red LEDs that is light emitting diode, LED, in case the abbreviation. So, you can make light emitting diodes, LEDs with red emission by gallium arsenic phosphide with phosphorus mole fraction equal to 0.4, because that is very popular in the desk calculators. Some of the calculators which people are using, that is also one very popular. Now, next thing that I would like to highlight here is the aspect of should we make use of, can we make use of this portion for making light emitting diodes? Because after all, for emitting light, what should be the wavelength? Visible light, anywhere from 0.4 to 0.7, 0.8 is 0.4 to 0.7, which would actually mean you need something like 0.31 or so. You need a wavelength which is corresponding to, actually you can work out, see, for visible light lambda should be 0.4 to 0.7 roughly microns. You can work out, you need about wave energy corresponding to that 1.24 divided by 0.4, that is about 3.1 electron volts, and 0.7 of course you will have 1.24 divided by 0.7. So, that you must have energies which are more than 1 electron volts. So, you can just work out and find out those things. What we are trying to point out is, if you go to this region, you have band gaps which are actually more than 1.977, more than 1.977 band gap you have got. That means, you will get, if I reduce that transition region, supposing I remove this diagram. Suppose I introduce into gallium arsenic phosphide 1 minus Y. For that, introduce nitrogen. Nitrogen as an impurity. Okay. Then what happens is EC and EV. Okay. If I vary Y, I vary this here. If I vary Y in this portion, it is indirect band gap, I am varying that band gap. Now, I introduce nitrogen as an impurity, which introduces a level very close to here, nitrogen level corresponding to the nitrogen impurity. Okay. Now, what will it do? If it is an indirect band gap semiconductor, you know that direct transition, you can't have light emission of the band gap. But if I introduce a level here, okay, then what I am doing is, let me remove this thing. What we are doing is, you are introducing a level here, which has a diffused momentum, in the sense you capture the electrons, destroy their momentum, it can capture the electron, destroy the momentum, then make a transition like this. Okay. So, it will capture here and then a transition. So, if I introduce a impurity like nitrogen, the momentum difference will be destroyed by that impurity level. Okay. So, once momentum level is destroyed, if this energy gap is sufficiently large, okay, I can get light in the visible region. So, okay, with that thing, what I am trying to point out now is, you can make use of this region, vary the band gap from 1.977 to 2.26 by varying Y. In each of those compounds, if you introduce nitrogen, that nitrogen introduces a level very close to the conduction band with some gap. That means, you get a transition which will emit light of energy which is close to this band gap. We have to repeat, if I move from here to here, I am varying the band gap. But in each one of those materials, if I introduce nitrogen, I will have an effective transition gap which is very close to that, but slightly smaller than that. Okay. If that is a thing, I can get a light out of it. In this transition, I can get light, I can make LED, which will give the wavelength corresponding to close to this. Okay. So, that is how they are able to make use of even gallium phosphide, which is 2.26, and add nitrogen impurity to that, okay, and then you get a wavelength corresponding to see, for example, if I take this as gallium phosphide, Y equal to 1, I am citing an extreme example. This is actually 2.26 and this is actually 0.05 electron volt. So, what you get there is actually how much? 2.21. What we are trying to point out is, gallium phosphide is indirect band gap, it will not emit light of the wavelength that you require, because it is not able to make the direct transition, but if you introduce a level like this, it will make a transition from in a two-step process where momentum is conserved in the first step, momentum is conserved in the first step. In the second step, the energy is conserved by emitting light, and that wavelength corresponds to 2.21 electron volts, and this one gives you lambda equal to 1.24 divided by 2.21 micron, and that turns out to be actually 0.56 micron. What is that? Anybody guess who is expert in wavelength? It is green. You can get, so you can make use of gallium phosphide, which is indirect bandgap semiconductor, add impurity like nitrogen, which introduces level at 0.05 below the conduction band, 0.05 electron volts, force a transition through that and force the emission of light. In fact, very high quantum efficiencies can be obtained. Okay. That is, for each photon making transition, each electron making transition, you can get light emitting. Okay. So, you can get wavelength corresponding to that which is green. So, if I use materials which are of different band gap here, if I use the materials which are of different band gap here, what I get is instead of 2.26 minus 0.05, I get here somewhere here 2 minus 0.05. So, you can get light of varying wavelength. So, you can, this is a very powerful material where you can get light from green, yellow, orange, red, entire wavelength you can get. So, red, orange, yellow, green. This is the whole idea is actually to the question is what is the criteria for selecting the impurity. To introduce the impurity, you should know where it will introduce the level. For example, in this case, this nitrogen is known to introduce impurity which is about 0.05 eV below the conduction band for all those materials. So, it is fortunate that you are able to force that light wavelength corresponding to this level and this. Now, let us just put that diagram. In fact, I will just put a series of diagrams now. Gallium phosphide. There, if I introduce a level like this here, nitrogen, the transition is corresponding to this, that is 2.21. If I choose somewhere here 1.9, if I choose somewhere here, that is 2.0, that is gallium, arsenic, Y, and Y is equal to something like 0.5 or so, some number I am just tossing out some number. Then what happens to band gap compared to here? Candid band gap is reduced. So, that is somewhere here. This does not change practically, the difference between the two. So, if that band gap reduces, nitrogen actually enjoys the same position, practically 0.05. So, the transition now is from here to here, which was that much, now has reduced. Energy has reduced, which means the wavelength has gone up. You go down here, you go from green to red. That is the idea. You can actually use some other impurities. For example, there is a very famous impurity which is used for making red light, red LED, that is zinc oxide. It is introduced into gallium phosphide, which introduces a trap level at the bottom. From at 0.3 EC minus 0.3. If I take this, if I introduce some other impurity, that will introduce impurity there, zinc oxide, that wavelength will be reduced. I am sorry, the energy will be reduced, wavelength will go up, we can force it to red light, 2.26 minus 0.3, that is the band gap transition. So, that is the thing. But now how good is the light, how much light is emitted for that particular wavelength depends upon how many impurities are present there. There may be unwanted impurities. Now, if you have unwanted impurities, I have put 2 levels here. Okay? When you put this level, you want to ensure, if you want red light, green light, you must have only the nitrogen impurity, because that wavelength. If I have one more impurity, what will happen? There will be some transition taken from through this. So, you will have unwanted emission. So, that is why when you make light emitting diodes, it is important that you have a pure material. The growth must be really pure, and you must be able to introduce the impurity which you want to introduce. That is the thing. Okay, now, this is about the gallium arsenic phosphide, where nitrogen actually gives you a quantum efficiency which is much higher when you introduce nitrogen here in the indirect band gap. Okay. In the sense, quantum efficiency means photons which are generated for the photons generated divided by whole electron pairs. For one whole electron pair which is recombining, for one whole electron pair which is recombining, how many photons are generated on an average? That is the thing. That is the quantum efficiency. Okay, for the light emitting diode. Now, there is one more very interesting application which actually we have been working out actually in our laboratory in IIT, that is detector. I am just citing out some of the applications when we are discussing this. You can use a material like gallium indium arsenide, if you go down here, okay, and make a detector which is suitable for optoelectronic applications. When you use a fiber optic communication, what do? You have the entire information transmitted through light. Now, ultimately at the receiving end, you must convert that light signal into electrical signal. There must be a detector. At the transmitting point, you must have a laser. At the receiving point, you must have a detector, and that detector should detect best at the wavelength that it comes from. So, for fiber optics, it is about 1.3 electron volts in that range. That is the best wavelength that people are using, okay, 1.3 to 1.5. Now, if you take gallium indium arsenide, okay, there what is happening is you have got, I will draw it a bit faster now, because you know this is X is mole fraction of gallium, and here you have got indium arsenide. X equal to 0 gives indium arsenide, x equal to 1 gives you gallium arsenide. Okay. Now, here you have got 0.36 band gap, 0.36 direct band gap, and gallium arsenide has got 1.43. Both are direct. You have got this is direct, that is also direct band gap. You mix them together, that is it. Choose the composition, you get the band gap, all direct. Okay. So, for example, if you use this as 0.47, use that as 0.47, then you get around 0.75. Okay. 0.75. The wavelength corresponding to that is actually equal to 1.653. Now, my question is, what we want to point out here is, this diagram is straightforward, no indirect. Okay. So, you can actually okay, you make a diode or make a diode like this. This is called detector. photodetector or a photodiode if you make, what you do is take indium phosphide N type. Okay. This is reverse of the LED. In the LED, what you do? You forward bias it, force recombination, light emission. In the detector, light is falling, it is absorbed and you get the current. Electron holes are generated, you reverse bias it, you get the current, draw the current out, not forward bias. So, and here what you do is a new P type or I type intrinsic or close to intrinsic, okay, indium, gallium, indium, arsenide of this composition, where X is 0.47. X is 0.47. If you choose that, you get a band gap of 0.73 electron, 0.75 electron volts, and this will be P plus gallium indium arsenide. Connected to, of course, you can bias it. Okay, you can bias it. This is a fiber. A fiber connected from this piece indium phosphide side. Okay. So, light is falling on this. The fiber is coupled to that. You must make arrangement to couple it together. The light is falling on that. Now, the idea is, if light is falling on that, what will happen when it falls on to indium phosphide? If I plot the photon current, can I take this off now? So, I will take this off now, put the other diagram. Okay. Remember this 0.75, lambda E is equal to 0.75 electron volts, lambda corresponding to that is 1.653 microns. What does it mean? What does it mean when I say for a detector the wavelength is 1.653 micron? It means actually like this, okay, which means if I have the band gap like this, if the light is falling, it should knock out electrons from here to here. It must create whole electron pairs, okay, when the light is falling on that. Now, whether it can knock out electrons or not depends upon energy. If the energy is less than 1.653 electron volts, okay, it will not knock out electrons. What will happen? It will be just be transmitted. Okay. If you take indium phosphide has got a cutoff wavelength which is actually about 0.92. Indium phosphide, this one, that is Eg is actually equal to 1.35 electron volts, which corresponds to lambda equal to 0.92 microns. Okay. Now, when the light is falling here into the from the back side, it sees the indium phosphide first. So, if the energies are greater than 1.35 electron volt, if the energy of the light that is coming is greater than 1.35 electron volts, which means if the wavelength is smaller than 0.93 electron volts, it will be absorbed. It will be absorbed by that. And this is a thick layer, this is very thin, 0.2 microns or 1 micron. So, if this is 100 microns or 200 microns, whatever light is falling here is absorbed here. It is just absorbed in the bulk. Whole electron pairs are there in the bulk. What happens if you generate whole electron pairs? They just recombine, fall back, no effect. Okay, that is all. It is converted into heat, light heat there, then it recombines. Okay. So, there is nothing happening there. But if the energy is more than that, or if the energy is less than that, if the energy is more than that, it will be absorbed. Okay. What we are telling is, quickly putting that diagram, Okay, if I see lambda versus current, if I connect it up like this, okay, reverse bias like this, there will be current versus lambda. If you say when the wavelength is 0.9, up to that point nothing is absorbed. When the wavelength becomes more than that, this will not absorb, this will act as a window, it will fall on this. Okay, this will absorb whenever the energy is right up to 0.7. So, up from 0.92 up to 1.6 microns, this layer will absorb. In fact, I think I should continue on this in my next discussion, more detailed. It will come like this. This is 1.65 angstroms. Okay. So, what I am trying to point out is, if the wavelength is small, this absorbs it, no effect. If the wavelength is more than that, this absorbs it, and that gives rise to current. If the wavelength is more than that, energy is less than that, no current. So, that is a very good window. We will continue on this particular discussion, few more aspects of this tomorrow or next lecture. Okay, thank you.